So here's something worth sitting with for a moment. Right now, tonight, as you're lying there getting comfortable, every atom in your body, every single one, was made inside a star. Not metaphorically, not poetically, although it is poetic, literally. The calcium in your bones, the iron in your blood, the oxygen you just breathed in, all of it was forged in the heart of a star that died before our sun was even born. You are, in the most concrete and scientific sense, made of ancient starlight. And the story of how that happened, how you went from nothing, truly nothing, to a conscious being lying in the dark listening to these words, well, that's the story of the entire universe. And it's a good one. So let's start at the very beginning, the actual beginning, before stars, before atoms, before light itself. Now, the first thing you have to appreciate is just how strange the very concept of a beginning is. We're so used to things having starts and ends. A movie begins, a road starts somewhere, your day had a morning. But when we talk about the beginning of the universe, we're talking about the beginning of time itself. Not an event that happened at a particular moment in time, but the moment that time switched on. Before that, and I'm using the word before loosely because it doesn't really apply, there was no before. There was no space to be empty. There was no clock ticking in a dark room. There was no dark room. The question, what happened before the Big Bang, is a bit like asking what's north of the North Pole. The question feels like it should have an answer, but the framework it's built on just doesn't extend that far. So, roughly 13.8 billion years ago, that's our best number, and it's a remarkably precise one. We've nailed it down to within about 40 million years, which sounds like a lot until you realize that's a margin of error of about 1/3 of 1%. 13.8 billion years ago, everything that exists, all matter, all energy, all of space itself, was compressed into a state so unimaginably dense and hot that our physics genuinely breaks down when we try to describe it. We can't actually narrate the very first instant, the first sliver of a second, because our equations produce infinities and nonsense. That's not a failure of imagination. It's an honest admission that our best theories, general relativity, quantum mechanics, stop working when you push them that far. They need to be unified into some deeper theory, a theory of quantum gravity, and we don't have that yet. So the very first moment remains a mystery, and anyone who tells you otherwise is selling something. But here's the thing. We can pick up the story astonishingly early. We're talking about the Planck epoch, named after Max Planck, the German physicist who sort of accidentally kicked off quantum mechanics around 1900. The Planck time is about 10 to the minus 43 seconds. That's a decimal point followed by 42 zeros, and then a 1. It's not a duration your brain can meaningfully grasp, and that's fine. The point is that before this moment, all 4 fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were probably unified into a single superforce. We think. We're not sure. But after the Planck time, gravity peeled away and became its own thing. And that separation, that symmetry breaking, is one of the most important ideas in all of physics. The universe, as it cooled, kept splitting unified things into distinct things. It's like watching a crystal form, structure emerging from formlessness. Let me slow down here because this idea of symmetry breaking deserves a moment. Think about water. Liquid water is symmetric. It looks the same in every direction. But when it freezes, it forms a crystal lattice, and suddenly there are preferred directions, a structure, a pattern. Something symmetric became something with distinct features. The early universe did this over and over again. Forces that were indistinguishable from each other at insane temperatures became separate and distinct as things cooled down. And each time a force separated out, the universe got more complex, more interesting. More things became possible. So after gravity splits off, we enter what's sometimes called the grand unification epoch, when the remaining three forces are still merged. This lasts until about 10 to the minus 36 seconds after the Big Bang. And then something extraordinary happens. The strong nuclear force separates from the electroweak force, and this transition may have triggered a period called cosmic inflation. Now, inflation is one of those ideas that sounds completely absurd until you realize it solves about 5 major problems in cosmology all at once, and then it starts to sound like it might be the most elegant idea anyone's ever had. Here's the problem inflation solves. When we look at the cosmic microwave background, and we'll get to what that is in a bit, we see that the temperature of the universe is almost exactly the same in every direction. The variations are tiny, on the order of 1 part in 100,000. But here's what's weird about that. Regions of the sky on opposite sides of our view are so far apart that in the standard model without inflation, light wouldn't have had time to travel between them since the Big Bang. They've never been in contact. They've never exchanged information or energy. So how can they be the same temperature? It's like walking into a room and finding that 2 cups of coffee on opposite ends of a mile-long table are exactly the same temperature to 5 decimal places and being told they were never in the same room together. That shouldn't happen. Unless, at some point very early on, they were in the same room. They were close enough to reach thermal equilibrium. And then the room expanded unbelievably fast, pulling them apart. That's inflation. In an almost incomprehensibly brief window, somewhere around 10 to the minus 36 to 10 to the minus 32 seconds. The universe expanded by a factor of at least 10 to the 26. Some models say much more. The observable universe went from something smaller than a proton to something about the size of a grapefruit. In a trillionth of a trillionth of a trillionth of a second. The expansion was faster than light, which sounds like it should be illegal, but here's the key. It's not objects moving through space faster than light. It's space itself stretching. And general relativity has no speed limit for the expansion of space itself. Objects embedded in that space get carried along for the ride, like raisins in rising bread dough. Each raisin isn't moving through the dough, but the distance between every pair of raisins is increasing because the dough itself is expanding. The physicist who first proposed inflation was Alan Guth, working at Stanford's Linear Accelerator Center in 1979. And the story goes that he was up late one night, working through the math, and when he realized the idea worked, that this period of exponential expansion could solve the horizon problem, the flatness problem, and the magnetic monopole problem all at once, he wrote in his notebook, in capital letters, "Spectacular realization," which is just a wonderful human moment. This guy, alone in his office, scribbling equations, and suddenly seeing the shape of the first fraction of a second of creation. He knew he'd found something. Now, inflation also does something else that's really beautiful, and this connects to why the universe has galaxies and stars and planets and you. During inflation, tiny quantum fluctuations, the kind of irreducible randomness that quantum mechanics tells us is woven into the fabric of reality, got stretched to cosmic scales. These fluctuations became slight variations in the density of matter and energy across the universe, Regions that were slightly denser would eventually pull in more matter through gravity, becoming the seeds of galaxies and galaxy clusters. Regions that were slightly less dense would become the great voids between them. So, the largest structures in the universe, clusters of galaxies stretching hundreds of millions of light years across, trace their origin to quantum jitters that happened when the universe was smaller than an atom. Think about that for a second. The quantum and the cosmic, connected by this moment of furious expansion. When inflation ended, the energy driving it was converted into a flood of particles and radiation, a process called reheating. And now the universe was hot. Unbelievably hot. Trillions of degrees. This is where the story becomes, in some ways, more familiar, because now we're dealing with particles and forces that our physics can describe quite well. The universe was a seething plasma of quarks, gluons, electrons, photons, neutrinos, a soup so energetic that particles and their antiparticles were constantly being created and annihilated in pairs. Energy becoming matter, becoming energy, over and over, in a roiling, blinding fog. And here's where one of the deepest mysteries in all of physics shows up. For every particle created, an antiparticle should have been created too. When a particle meets its antiparticle, they annihilate each other, converting back into pure energy. So in principle, every bit of matter should have been canceled out by an equal amount of antimatter, leaving a universe of nothing but radiation. No atoms, no stars, no you. But that's not what happened. For reasons we still don't fully understand, there was a tiny asymmetry. For every billion antimatter particles, there were 1,000,000,001 matter particles, one extra particle in 1,000,000,000. And when all the annihilation was done, that tiny surplus, that 1 in 1,000,000,000 remainder, is everything. Every galaxy, every star, every planet, every grain of sand, every cell in your body. We exist because of a rounding error in the laws of physics. We think this asymmetry has something to do with a subtle difference in how the weak nuclear force treats matter and antimatter, something called CP violation. But the known sources of CP violation aren't nearly large enough to account for the surplus we observe. It's one of the great open questions. By about 1 microsecond after the Big Bang, that's a millionth of a second, the universe had cooled enough for quarks to bind together into protons and neutrons. This is called the quark-hadron transition, and it's a bit like steam condensing into water droplets. Above a certain temperature, quarks roam free in a quark-gluon plasma. Below it, they're permanently confined inside composite particles. The strong nuclear force, which is the force responsible for this, has a peculiar property. It gets stronger as quarks move apart. Imagine two quarks connected by a rubber band that gets thicker the more you stretch it. Eventually, it's easier to create new quarks from the vacuum than to keep stretching. So quarks are always locked up in groups of 2 or 3. Protons, 2 up quarks and 1 down quark. Neutrons, 2 down quarks and 1 up quark. These are the building blocks that will eventually make atomic nuclei. Now the universe is about a second old. 1 second. And already so much has happened. Forces have separated. Inflation has stretched space beyond recognition. Matter has survived its war with antimatter. Quarks have condensed into protons and neutrons. The temperature is about 10 billion degrees, which is roughly the temperature at the center of a massive star going supernova. And at this temperature, something important is happening. Neutrinos are decoupling from everything else. Neutrinos are these ghostly particles that barely interact with anything. Right now, as you lie there, About 65 billion neutrinos from the sun are passing through every square centimeter of your body every second, and they sail right through as if you aren't there. At 1 second after the Big Bang, the universe became transparent to neutrinos. They stopped interacting with the rest of the matter and just streamed outward. Those neutrinos are still out there, forming a cosmic neutrino background that's even older than the cosmic microwave background. We haven't directly detected it yet. The energies are incredibly low. But we know it's there, and detecting it is one of the holy grails of observational cosmology. And now, with the universe a few minutes old, we arrive at one of the most precisely confirmed predictions in all of science: Big Bang nucleosynthesis. This is the period, lasting from about 10 seconds to roughly 20 minutes after the Big Bang, when protons and neutrons fuse together to form the first atomic nuclei. Not atoms yet. Atoms need electrons in orbit, and the universe is still far too hot for that. But nuclei. And here's what's remarkable about this. We can calculate exactly what should have been produced. And when we look out at the oldest, most pristine gas clouds in the universe, the ones that haven't been contaminated by later stellar processes, the abundances match. About 75% hydrogen by mass, about 25% helium-4, with trace amounts of deuterium, helium-3, and a tiny, tiny bit of lithium-7. The agreement between prediction and observation is extraordinary, and it's one of the strongest pieces of evidence that the Big Bang model is correct. It's not a guess. It's not a rough sketch. It's a precise quantitative prediction that lines up with what we actually see in the real universe, and that kind of agreement doesn't happen by accident. Now, there is one small wrinkle in this beautiful picture, and it's worth mentioning because science is honest about its loose threads. The predicted amount of lithium-7 is actually a bit higher than what we observe in the oldest stars. It's called the cosmological lithium problem, and it's been bugging astrophysicists for decades. The discrepancy isn't huge, but it's persistent, and nobody's entirely sure what's going on. Maybe the oldest stars have processed their lithium in ways we don't fully understand. Maybe there's some subtle nuclear physics we're getting slightly wrong. Maybe, and this is the more exciting possibility, it's a hint of new physics beyond the standard model. But for now, it's a small blemish on an otherwise stunning success story. And honestly, the fact that we can sit here and argue about the precise abundance of a trace element forged in the first 20 minutes of existence, that itself is kind of incredible, right? So, the first 20 minutes are over. The universe has done something astonishing. It's built the raw nuclear material that will eventually become everything. Hydrogen and helium nuclei, drifting in a sea of free electrons and photons. But here's the thing. We're nowhere near done, because right now, the universe is still a blinding, opaque fog. You couldn't see through it if you tried, and it's going to stay that way for a very, very long time. Let's talk about why. Picture the universe at this stage. It's a hot, dense plasma. That word plasma just means a gas, where the electrons have been stripped away from atomic nuclei. So you've got charged particles flying around everywhere. And photons, light, can't travel far in a plasma like this. A photon gets emitted, travels a tiny distance, and then slams into a free electron and gets scattered in a random direction. It's like trying to see through the thickest fog you've ever experienced, except infinitely worse. Every photon is bouncing around like a pinball, never getting anywhere. The universe is technically full of light, absolutely flooded with it. But that light is trapped. It can't stream freely. Matter and radiation are locked together in this intimate, chaotic dance. And this goes on, and on. For hundreds of thousands of years, the universe is expanding, cooling, but still opaque. Still a plasma. Still this roiling, glowing fog where light and matter are tangled up together. If you could somehow exist inside it, you wouldn't see stars or galaxies or anything recognizable. You'd just see a uniform, brilliant glow in every direction, impossibly bright, gradually dimming and reddening as the temperature slowly drops. Now, during this long era, something subtle but important is happening inside that plasma. Remember those tiny density fluctuations we talked about? The quantum ripples from inflation that got stretched to cosmic scales. They're not just sitting there, they're evolving. Regions that are slightly denser than average have slightly stronger gravity, so they're pulling in a little more matter. But the radiation pressure, the photons bouncing around inside the plasma, is pushing back. So you get these waves. Literally, sound waves. Pressure waves rippling through the plasma of the entire universe. The denser regions compress, the photon pressure pushes back, they expand, gravity pulls them in again, and you get this oscillation. Cosmologists call them baryon acoustic oscillations, which is a fancy way of saying the universe is ringing like a bell. Think about what that means. The entire cosmos, hundreds of thousands of years old, is vibrating. It has a sound, not sound you could hear with your ears. The frequencies are absurdly low, with wavelengths spanning tens of thousands of light years. But it's the same physics as sound in air. Compression and rarefaction, pressure waves moving through a medium. The universe is humming to itself in the dark. And those oscillations matter, because they're going to leave an imprint, a fingerprint, one that we can still read today, billions of years later. But I'm getting ahead of myself. Let's stay in this fog a little longer. The temperature is dropping. When the universe was 20 minutes old, it was about 1 billion degrees. But it keeps cooling as space expands. After a few thousand years, it's down to millions of degrees. After tens of thousands of years, hundreds of thousands of degrees. And somewhere around 380,000 years after the Big Bang, give or take, the temperature finally drops to roughly 3,000 Kelvin, about the temperature of the surface of a cool red star. And at that temperature, something transformative happens. Electrons slow down enough to be captured by nuclei. For the first time, hydrogen atoms form, complete atoms. A proton with an electron bound to it. Helium atoms too. This process is called recombination, which is a slightly misleading name because the electrons and nuclei were never combined before. This is the first time. But the name stuck. And here we are. And here's why recombination changes everything. Once the electrons are locked into atoms, they're no longer free to scatter photons. Suddenly, the universe goes from opaque to transparent, almost like a switch being flipped. The fog lifts. Light, for the first time in 380,000 years, can travel freely through space. Photons that had been bouncing around endlessly in the plasma are suddenly released. They stream outward in every direction, carrying with them a snapshot, a baby picture, of the universe at that exact moment. Those photons are still traveling. They've been traveling for 13.8 billion years, and we can detect them. This is the cosmic microwave background, the CMB, and it is, without exaggeration, one of the most important observations in the history of science. It was first detected accidentally in 1964 by 2 radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson. They were working with a large horn antenna that had been built for satellite communication, and they kept picking up this persistent, low-level noise, a faint hiss that they couldn't get rid of. They checked everything. They recalibrated the instrument. They even cleaned pigeon droppings out of the antenna, thinking that might be the source. But the noise wouldn't go away. It was coming from everywhere in the sky, equally, at all times. It didn't change with the seasons or the time of day. It was just there. Meanwhile, not far away at Princeton University, a group of physicists led by Robert Dick and Jim Peebles had been building their own antenna specifically to search for this signal. They had predicted it. They knew that if the Big Bang model was correct, there should be a faint afterglow, ancient light from the moment of recombination, stretched by the expansion of the universe from its original visible light wavelengths all the way down into the microwave part of the spectrum. They were getting ready to look for it. And then they got a phone call from Penzias and Wilson, who had found it by accident. There's a wonderful, slightly bittersweet irony to this story. Penzias and Wilson won the Nobel Prize in 1978 for the discovery. Dickey and Peebles, who understood what it was and had predicted it, didn't share in that particular prize, though Peebles eventually won his own Nobel in 2019 for his broader contributions to cosmology. Science can be a little unfair that way sometimes, but the discovery itself, that's what matters. The CMB is radiation with a temperature of about 2.725 Kelvin. That's 2.725 degrees above absolute zero. Incredibly cold. But it's everywhere. It fills all of space. It's the oldest light in the universe, and when you tune an old analog television to a channel with no broadcast, a small percentage of that static on the screen is actually the cosmic microwave background. You're literally watching the afterglow of creation. And here's what's really beautiful about it. When we measure the CMB very precisely, and we have, with satellites like COBE in 1989, WMAP in 2001, and Planck in 2009, we find that it's almost perfectly uniform, almost exactly the same temperature in every direction, but not quite. There are tiny, tiny fluctuations, variations of about 1 part in 100,000, slightly warmer spots and slightly cooler spots. And those fluctuations are the imprint of those sound waves we were talking about. The baryon acoustic oscillations ringing through the plasma before recombination. The slightly denser regions, where matter had been compressed by the acoustic waves at the moment the fog cleared, show up as very slightly warmer spots. The less dense regions show up as cooler spots. This is the fingerprint. This is the pattern that tells us almost everything we know about the large-scale properties of the universe. By analyzing the sizes and distributions of those tiny hot and cold spots, cosmologists have extracted an astonishing amount of information: the age of the universe, its geometry, how much of it is ordinary matter, how much is dark matter, how much is dark energy, the rate of expansion. It's all encoded in that faint, ancient glow. The CMB is like a cosmic Rosetta Stone, and learning to read it has been one of the great intellectual achievements of the past 50 years. So now the fog has lifted. The universe is transparent. Light is streaming freely for the first time. Atoms exist. But here's the thing. There are no stars yet, no galaxies, no sources of new light. The CMB photons are redshifting, losing energy as space expands, and the universe is getting dimmer, and dimmer, and dimmer. What comes next is an era that cosmologists call, with a certain poetic accuracy, the Dark Ages. For perhaps 100 million years, maybe 200 million, the exact duration is still being refined, the universe is dark, genuinely dark. There's hydrogen gas everywhere, and helium, and dark matter forming an invisible scaffolding of gravitational structure. Those tiny density fluctuations from the CMB are still there, still growing. Gravity slowly pulling matter into denser and denser clumps. But nothing is shining. No fusion is happening. The universe is a vast, quiet, expanding darkness, and the only light is the fading afterglow of the CMB, now shifted well below visible wavelengths. It's a strange and haunting period to think about. The universe has all the ingredients for everything that will come, for stars, for planets, for you, but it hasn't assembled them yet. It's like a darkened stage before the performance begins, all the actors waiting in the wings. And what ends the dark ages, what lights the stage for the first time, is the birth of the very first stars. And those first stars were nothing like the stars we know today. They were monsters, absolute titans. The first generation of stars, astronomers call them population 3 stars, which is a little confusing because the numbering goes backwards, a historical quirk of how stellar classification developed. These first stars were almost certainly enormous. We're talking perhaps 50 times the mass of our sun, 100 times, maybe even 300 times. Some theoretical models suggest individual stars that were 1,000 solar masses, though that's pushing toward the extreme end of what the physics allows. The reason they were so massive comes down to chemistry, or rather, the lack of it. See, when a cloud of gas collapses under gravity today, in our modern universe, it fragments into smaller and smaller pieces as it falls inward. And the reason it fragments is that the gas can cool efficiently. There are carbon atoms and oxygen atoms and dust grains, all the stuff that was forged in previous generations of stars. And these act like tiny radiators, emitting infrared light, bleeding away thermal energy, letting the gas cool and condense into relatively small, dense clumps. That's how you get stars like our sun, which is honestly a pretty modest star. But back in the Dark Ages, none of that stuff existed. The gas was almost entirely hydrogen and helium, with just traces of lithium and deuterium. And hydrogen and helium are terrible at cooling. They're simple atoms. They don't have the complex electron energy levels that carbon and oxygen do, the ones that let those heavier atoms radiate away heat so efficiently. So when those primordial gas clouds started collapsing, pulled together by the gravitational scaffolding of dark matter, the gas got hot, and it couldn't cool down very well, and it couldn't fragment into small pieces. Instead, you got these massive bloated clouds collapsing into single enormous objects, or maybe small groups of very large objects. The first stars were giants because the universe hadn't yet invented the tools to make small ones. And here's what's really fascinating about these first stars. Because they were so massive, they burned through their nuclear fuel at an absolutely ferocious rate. A star like our sun will burn steadily for about 10 billion years. It's middle-aged right now, roughly 4.6 billion years into its life, with plenty of fuel left. But a star that's 100 times more massive doesn't live 100 times shorter. It lives millions of times shorter, because the rate of fusion scales so steeply with mass. Those first stars probably lived for only 2 or 3 million years. Some of them may be less. In cosmic terms, that's a blink. The universe waited 100 million years in darkness for these stars to form, and then they burned through their entire lives in a couple of million years. Fast, bright, and violent. But oh, what they accomplished in that brief time. Inside those massive cores, temperatures and pressures were so extreme that nuclear fusion didn't stop at helium the way it does in smaller stars. These stars fused hydrogen into helium, yes, but then they fused helium into carbon, carbon into oxygen, oxygen into neon, neon into magnesium, all the way up the periodic table in a series of nested fusion shells, like layers of an onion, each shell burning a heavier element than the one above it. And at the very center, in the final days of the star's life, silicon fused into iron. And iron, this is a beautiful piece of physics. Iron is the end of the line. Iron has the most tightly bound nucleus of any element. You can't extract energy by fusing iron into something heavier. It actually costs energy. So when the core fills with iron, fusion stops. And when fusion stops, the core loses the outward pressure that was holding up the entire star against its own gravity. And in less than a second, literally less than a second, the core collapses. What happens next is one of the most energetic events in the universe. The core implodes. The outer layers come crashing inward. They hit the incompressibly dense core and bounce, and the result is a supernova. But not just any supernova. For the very first stars, especially the most massive ones, these were likely pair instability supernovae, a specific type of explosion where the temperatures in the core get so high that photons spontaneously convert into pairs of matter and antimatter, electrons and positrons, and this conversion removes pressure support so suddenly that the entire star is disrupted. Not just the outer layers, the entire star. There's no remnant left behind, no neutron star, no black hole. The whole thing is blown apart and scattered into space. And all those heavy elements that were forged in the star's core, the carbon, the oxygen, the silicon, the iron, all of it gets ejected into the surrounding gas, enriching it, seeding it with the raw materials for the next generation of stars, and for planets, and eventually for you. Think about what that means for a moment. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now. None of that existed at the beginning. It was all manufactured inside stars, and it was delivered to the surrounding universe by explosions. You are, quite literally, made of recycled stellar debris. Carl Sagan said it beautifully. We are star stuff. But it's not poetry. It's a factual description of nucleosynthesis and supernova enrichment. Every atom of carbon in your body was once inside a star that no longer exists. Now, these first supernovae didn't just scatter heavy elements. They also did something else that was crucial. They blasted shock waves through the surrounding gas, compressing it, triggering new rounds of collapse and star formation. And this next generation of stars, forming from gas that was now lightly enriched with heavier elements, could cool more efficiently. They could fragment into smaller pieces. They could form stars that were less massive, longer lived, more varied. This is the transition from population 3 to population 2 stars, the second generation, born from enriched gas. And some of these stars were small enough and long-lived enough that a few of them are still burning today, 13 billion years later. We've actually found some of them. Stars in the halo of our Milky Way galaxy with incredibly low but non-zero amounts of heavy elements. Stars like SMS SJ 031300.36-6, 70839.3, which has a wonderfully unwieldy catalog name, but an extraordinary story. It was discovered in 2014 by a team led by Stefan Keller at the Australian National University, and its iron content is so low that it's essentially undetectable. But it has detectable carbon, which is a signature that it formed from gas enriched by one of those very first pair instability supernovae. It's like finding a living fossil, a star that carries the chemical fingerprint of the universe's very first generation of light. And while individual stars were being born and dying, something larger was happening. Those dark matter halos, the gravitational scaffolding I mentioned, were merging with each other, growing bigger, pulling in more gas, forming larger and larger structures. The first stars didn't form in isolation. They formed in small clusters within small dark matter halos, and those halos were drawn together by gravity into bigger halos, which pulled in more gas, which formed more stars, and gradually, over hundreds of millions of years, these growing clumps of dark matter and gas and stars became the first galaxies. Now, calling them galaxies is a bit generous at first. They were nothing like the grand spirals you see in Hubble photographs. The earliest proto-galaxies were small, irregular, clumpy collections of stars and gas, maybe a few million stars at most, compared to the hundreds of billions in a modern galaxy like the Milky Way. But they were the seeds, and they kept merging, kept growing, kept forming new stars from the enriched gas that previous generations had seeded with heavy elements. Galaxy formation is fundamentally a hierarchical process. Small things merge to make bigger things, which merge to make bigger things still. It's gravity doing what gravity does, patient and relentless, working on timescales that make human history look like a single frame in a very long film. And here's where something dramatic happens that we're only now beginning to understand in detail, thanks to telescopes like the James Webb Space Telescope, which launched on Christmas Day 2021 and started delivering science data in 2022. The JWST was designed specifically to see this era, the epoch of reionization, as it's called. Because those first stars and first galaxies didn't just produce light, they produced ultraviolet light. Lots of it. And ultraviolet photons are energetic enough to ionize hydrogen, to strip the electron away from the atom entirely. So, as the first sources of light turned on, they began to ionize the neutral hydrogen gas around them, creating expanding bubbles of ionized gas in the otherwise neutral medium. Imagine the universe as a vast fog of neutral hydrogen, and each new star or galaxy is like a lantern being lit, burning away the fog in an expanding sphere around it. At first, the bubbles are small and isolated, but as more and more sources turn on, the bubbles grow, they overlap, they merge, and eventually, somewhere around 500 million to a billion years after the Big Bang, the exact timing is still being pinned down. The bubbles have merged completely, and the entire universe is reionized. The fog is gone for good. The universe is transparent again, but this time it's transparent because the gas is ionized, not because it's neutral. This is one of the last great phase transitions of the universe, from neutral to ionized, and it marks the end of the cosmic dark ages in the fullest sense. The universe is now lit up. Galaxies are forming and growing. Stars are living and dying and enriching the gas with heavier and heavier elements, each generation building on the chemical legacy of the ones before. And within those galaxies, something else is starting to happen, something quieter, but in some ways even more consequential. Around the densest, most active regions, around the centers of galaxies where gas is funneling inward most aggressively, black holes are growing. Not the stellar mass black holes left behind by individual supernovae, but something much larger. Supermassive black holes, millions or even billions of times the mass of the Sun, sitting at the hearts of galaxies and shaping everything around them. These aren't just passive objects sitting there in the dark. They're engines. They're some of the most powerful engines the universe has ever produced, and the story of how they got so big, so fast, is one of the genuine mysteries that keeps astrophysicists up at night, which, given that we're lying here in the dark together, feels kind of appropriate. Here's the puzzle. We've found supermassive black holes that already contain 1 billion solar masses when the universe is less than 1 billion years old. Think about that timeline. The universe is barely getting started, cosmically speaking, and already there are objects out there that have somehow accumulated the mass of 1 billion suns into a region smaller than our solar system. How? How do you grow something that enormous that quickly? Because black holes, despite their reputation, can't just swallow everything around them instantaneously. There's a speed limit. It's called the Eddington limit, named after Arthur Eddington, the same brilliant astrophysicist who confirmed Einstein's general relativity during the 1919 solar eclipse. The idea is straightforward. As matter falls toward a black hole, it heats up. It heats up enormously, to millions of degrees, and that hot matter radiates energy outward. Light, X-rays, just tremendous amounts of radiation pouring out. And that radiation pushes back against the infalling material. So the black hole is trying to pull stuff in, but the very act of pulling stuff in generates radiation that pushes stuff away. There's a balance point, a maximum rate at which the black hole can accrete matter. And if you do the math, even feeding at that maximum rate continuously from the moment the universe began, it's genuinely difficult to grow a stellar mass seed black hole. Say, a few tens of solar masses, the kind left behind by a single dying star, into 1 billion solar mass monster in under 1 billion years. The numbers just barely work, and that's assuming the black hole is feeding at maximum capacity nonstop, which is unlikely in the messy, turbulent reality of a young galaxy. So people have proposed alternatives. Maybe the seeds weren't small. Maybe instead of starting with a stellar mass black hole from a single supernova, some of these early black holes formed from the direct collapse of enormous clouds of gas. Tens of thousands, or even 100,000 solar masses collapsing directly into a black hole without ever forming a normal star first. These are called direct collapse black holes, and the conditions required are pretty specific. You need a massive cloud of pristine gas, mostly hydrogen, with very little ability to cool and fragment into smaller clumps. If the gas can't cool efficiently, it can't break up into individual stars. Instead, the whole cloud just contracts and contracts, getting denser and hotter until it crosses a threshold and collapses into a black hole in one catastrophic event. It's a beautiful idea, and it gives you a much bigger seed to start with, which makes the growth timeline much more comfortable. But whether this actually happened, whether the conditions in the early universe were right for direct collapse on a large scale, that's still being debated. We haven't directly observed one of these events. Not yet. And then there's another possibility, which is that maybe the Eddington limit can be exceeded. Maybe in certain geometries, certain configurations of infalling gas, the radiation doesn't push back as effectively, and the black hole can feed faster than the classical limit would suggest. This is called super-Eddington accretion, and there's growing theoretical support for it, especially in cases where the infalling material forms a thick puffy disk rather than a thin one, so the radiation gets trapped and carried inward along with the gas, instead of escaping to push material away. It's messy and complicated, and the simulations are still being refined, but it's a real possibility. The truth is probably some combination of all of these: bigger seeds, occasional super-Eddington feeding, and mergers between black holes as their host galaxies collide and combine. And this brings us to something genuinely spectacular: active galactic nuclei, or AGN, and their most extreme manifestation, quasars. When a supermassive black hole is actively feeding, when gas is spiraling inward, heating up, radiating furiously, the region around that black hole can outshine the entire rest of the galaxy. The entire galaxy. 100 billion stars. And this tiny region at the center, smaller than our solar system, is brighter than all of them combined. These are quasars, and when they were first discovered in the early 1960s, nobody knew what they were. They looked like stars in photographs, point-like sources of light, but their spectra were bizarre, with emission lines that didn't match any known element. It was Martin Schmidt, a Dutch-American astronomer at Caltech, who figured it out in 1963. He realized the emission lines were actually familiar hydrogen lines, but redshifted by an enormous amount. These objects weren't nearby stars at all. They were incredibly distant, billions of light years away, which meant they had to be unimaginably luminous to appear as bright as they did. And the only mechanism anyone could come up with to explain that kind of luminosity from such a compact region was matter falling into a supermassive black hole. That realization, that the centers of galaxies could harbor these monstrous engines of light and energy, changed our understanding of galaxies forever. And here's what's really interesting. We now think that most large galaxies, maybe all of them, have a supermassive black hole at their center. Our own Milky Way has one. It's called Sagittarius A star. It's about 4 million solar masses, and right now it's relatively quiet, not actively feeding much, just sitting there. But in the past, it was probably more active. And in 2022, the Event Horizon Telescope collaboration released an image of it. Well, not an image of the black hole itself, since black holes don't emit light, but an image of the glowing ring of superheated gas swirling around it, the shadow of the event horizon silhouetted against that glow. They'd done the same thing for the much larger black hole in the galaxy, M87, back in 2019. That was the first ever image of a black hole's shadow, 6.5 billion solar masses. A true monster. And then they turned the same technique on our own galactic center. It's a remarkable thing to have a picture of the gravitational heart of our own galaxy. But let's pull back from black holes for a moment, because while they're growing and feeding and occasionally blazing as quasars, the galaxies around them are evolving too, and the universe is entering what you might call its most productive era. We're now in the first few billion years after the Big Bang, and galaxies are forming, merging, growing, and the rate of star formation across the universe is climbing. It will eventually peak. The cosmic star formation rate hits its maximum somewhere around 2 to 3 billion years after the Big Bang, roughly 10 to 11 billion years ago. And then it begins a long, slow decline that continues to this day. We're living in the universe's quiet retirement, in a sense. The glory days of star formation are behind us. But during that peak, galaxies were furiously converting gas into stars, and the chemical enrichment of the universe was accelerating with every generation. And this is where we need to talk about something that sounds mundane, but is actually one of the most important stories in the entire history of the cosmos, the origin of the elements heavier than iron. Because remember, stellar fusion can build elements up to iron, and iron is where it stops. The binding energy per nucleon peaks at iron 56, so fusing iron into heavier elements doesn't release energy. It costs energy. Stars can't do it through their normal burning processes. So where does everything heavier than iron come from? The gold in a ring? The uranium in a reactor? The iodine in your thyroid? The barium in medical imaging? Where does all of that originate? The answer has been understood in broad strokes since a landmark 1957 paper by Margaret Burbidge, Geoffrey Burbage, William Fowler, and Fred Hoyle, known affectionately as B²FH, or just the B2FH paper. They laid out the processes of stellar nucleosynthesis in extraordinary detail, and for elements heavier than iron, the key mechanisms are neutron capture processes. The idea is elegant. You take an existing nucleus, say an iron nucleus, and you bombard it with neutrons. Neutrons have no electric charge, so they don't get repelled by the positive charge of the nucleus. They can just waltz right in and stick. Now you've got a heavier isotope. If that isotope is stable, great. It just sits there, and maybe it captures another neutron, and another, building up to heavier and heavier isotopes. But if the isotope is unstable, if it's radioactive, then a neutron inside the nucleus will eventually decay into a proton, emitting an electron and an antineutrino in the process. That beta decay transforms the element into the next one up on the periodic table. And then that new element can capture more neutrons, and the process continues, building heavier and heavier elements step by step. There are two versions of this. The slow process, the S process, happens inside certain evolved stars, particularly asymptotic giant branch stars, where the neutron flux is moderate and there's plenty of time between neutron captures for unstable isotopes to decay. The S process builds up elements along a specific path through the chart of Nuclides, producing things like strontium, barium, and lead. But the rapid process, the R process, requires an environment so extreme, so flooded with neutrons, that nuclei capture neutrons faster than they can decay. The nucleus just piles on neutron after neutron in a frenzy, reaching incredibly neutron-rich, unstable isotopes that then decay back toward stability, producing a different set of heavy elements: gold, platinum, uranium, thorium, europium. For decades, the site of the R process was assumed to be core collapse supernovae. It made sense intuitively. Supernovae are violent, energetic, and involve tremendous numbers of neutrons. But as the simulations got better, as the models became more sophisticated, it became harder and harder to get the conditions right. The neutrino-driven winds from a newly formed neutron star just didn't seem to provide quite the right neutron-to-proton ratio, quite the right entropy, to produce the heaviest R process elements in the quantities we observe. Something else was needed. And then came August 17, 2017. That's a date worth remembering. The LIGO and Virgo gravitational wave detectors picked up a signal designated GW170817, and it was different from the black hole mergers they'd detected before. The signal lasted longer, about 100 seconds of in-spiral, and the frequency range indicated lower masses. This wasn't two black holes. This was two neutron stars spiraling toward each other and merging about 130 million light-years away in a galaxy called NGC 4993. And within 2 seconds of the gravitational wave signal, the Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same part of the sky. And then, over the following hours and days and weeks, telescopes around the world, optical, infrared, ultraviolet, radio, X-ray, all turned to look at the same spot, and they watched a new kind of transient event unfold. A kilonova. The material flung outward by the merger was glowing, heated by the radioactive decay of freshly synthesized heavy elements, and the spectral signatures were consistent with R process elements, lanthanides, heavy metals, exactly the kind of nuclei that had been so hard to produce in supernova models. It was one of those moments in science where multiple lines of evidence converge at once and the picture suddenly snaps into focus. Neutron star mergers are a major site, possibly the dominant site, of our process nucleosynthesis. The gold in your jewelry, the platinum in a catalytic converter, may well have been forged in the collision of two dead stars, each one the compressed remnant of a star that lived and died billions of years ago, spiraling together over millions of years until they finally met in a cataclysm that lasted milliseconds and scattered heavy elements across light years of space. That material mixed into gas clouds. Those gas clouds formed new stars and planets, and eventually some of those atoms ended up here, on Earth, in your body. The calcium in your bones was made in a star. The iron in your blood was made in a star, and the iodine in your thyroid may have been made when two neutron stars collided somewhere in our galaxy, billions of years before the sun was born. So by the time the universe is a few billion years old, the periodic table is filling in, the chemical palette available for planet building, and eventually, life is getting richer with every passing generation of stars. And the galaxies themselves are maturing, developing structure, settling into the shapes we recognize today. Some become grand spirals like our Milky Way, with elegant arms of gas and young stars winding outward from a central bulge. Others become ellipticals, smooth and round, dominated by old red stars, their gas largely exhausted or expelled. The process of galaxy evolution is shaped by mergers. When two galaxies collide, which happens frequently in the early universe when everything is closer together, the gravitational interaction can trigger enormous bursts of star formation, rearrange the structure entirely, and feed the central black hole. Our own Milky Way has a long history of absorbing smaller galaxies, and it's still doing it today. The Sagittarius dwarf elliptical galaxy is being tidally shredded and absorbed right now, its stars being stretched into long streams that wrap around our galaxy like threads being wound onto a spool. And in about 4.5 billion years, the Milky Way will collide with the Andromeda Galaxy, our nearest large neighbor, currently approaching at about 110 kilometers per second. The two will merge into a single large elliptical galaxy, sometimes nicknamed Milkdromeda, though the individual stars are so widely spaced that actual stellar collisions will be extraordinarily rare. It'll be more like two swarms of bees passing through each other. But that's the far future. Let's come back to the past, because something very specific is happening about 9 billion years after the Big Bang, about 4.5 billion years ago, in an unremarkable arm of an unremarkable spiral galaxy. A cloud of gas and dust, enriched by generations of stellar nucleosynthesis, and perhaps triggered to collapse by the shock wave of a nearby supernova, begins to contract under its own gravity. It's not a particularly large cloud, and there's nothing obviously special about it. But as it contracts, it spins faster. Conservation of angular momentum, the same reason a figure skater spins faster when they pull their arms in. And it flattens into a disk, and at the center, the density and temperature climb higher and higher until something extraordinary happens. The temperature at the core of that collapsing cloud reaches about 10 million degrees Kelvin, and at that threshold, hydrogen nuclei, protons, are moving so fast, slamming into each other with such ferocity that they overcome their mutual electrical repulsion and fuse. 4 hydrogen nuclei become one helium nucleus, and a tiny bit of mass is converted into energy according to that famous equation you already know. And just like that, a star is born. Our star, the Sun. It's about 4.6 billion years ago, and when the Sun ignites, it's not alone. It's surrounded by that flattened disk of leftover gas and dust, spinning around it like a cosmic frisbee. And this disk is where everything else in our solar system is going to come from. Every planet, every moon, every asteroid, every comet, every grain of dust on every rocky world, all of it starts here, in this protoplanetary disk. And the process by which a flat disk of gas and dust becomes a collection of distinct worlds is one of the most fascinating and, honestly, one of the most hard-won stories in all of science. Because for a long time, we really struggled to figure out how it works. The basic idea goes back surprisingly far. Immanuel Kant, the philosopher. Yes, that Kant, the one you might associate with moral imperatives and dense metaphysics, proposed in 1755 that the solar system formed from a rotating cloud of gas. Pierre-Simon Laplace independently developed a similar idea in 1796, and together their concept became known as the nebular hypothesis. And the broad strokes were right. They were remarkably right for the 18th century. But the details, how you actually get from a smooth disk of gas to discrete, round planets orbiting at specific distances, that took another 2 centuries to work out, and honestly, we're still refining the picture. Here's the basic challenge. You've got this disk, and it's mostly hydrogen and helium, because that's what the universe is mostly made of. But sprinkled through it are heavier elements, carbon, oxygen, silicon, iron, all those gifts from previous generations of stars. Close to the young sun, where it's hot, only materials with high melting points can exist as solids, metals and silicate minerals, basically rocks. Farther out, where it's cooler, you cross what's called the frost line or the snow line, beyond which water can exist as ice, and beyond that, ammonia ice, methane ice, carbon dioxide ice. This temperature gradient is why our solar system has the structure it does. Small rocky planets close in, gas and ice giants farther out. It's not random, it's thermodynamics. But how do you go from microscopic dust grains to full-sized planets? This is where it gets genuinely tricky, and there's a famous problem in planetary science called the meter-size barrier. Tiny dust, grains, we understand. They collide gently and stick together through electrostatic forces, the same way dust bunnies form under your bed. They build up into pebbles, centimeter-sized clumps, no problem. But once objects reach roughly a meter across, things go wrong. At that size, they're too big for electrostatic forces to hold them together on collision, but too small for gravity to matter. And they're experiencing aerodynamic drag from the gas in the disk, which causes them to spiral inward toward the sun on timescales of just a few hundred years. So you've got these meter-sized objects that should either shatter when they collide or fall into the sun before they can grow. How do you get past that? One of the most promising answers came from a mechanism proposed by several researchers but formalized in a landmark 2005 paper by Andrew Uden and Jeremy Goodman called the streaming instability. The idea is elegant. As those pebble-sized particles drift inward through the gas, they naturally clump together in certain regions due to the interaction between the particles and the gas. It's a feedback loop where a slight concentration of particles reduces the local headwind, which causes particles to drift more slowly there, which causes more particles to pile up, which reduces the headwind further. The clumps grow denser and denser until gravity takes over, and suddenly you've leapfrogged right past the meter-size barrier. You go from pebbles to objects tens or hundreds of kilometers across in what might be a remarkably short time. These are called planetesimals, and once you have planetesimals, you're in business, because now gravity is the dominant force and things can grow by pulling in neighbors. From planetesimals, you get what's called runaway growth. The biggest objects in a region have the strongest gravity, so they sweep up material faster than their smaller neighbors, and the rich get richer. A planetesimal that's slightly larger than its neighbors grows faster, which makes it larger still, which makes it grow even faster. Within maybe 100,000 years, which sounds like a long time but is a blink in cosmic terms, you end up with a handful of objects roughly the size of the Moon to Mars in each region of the disk. These are called planetary embryos or protoplanets. And then comes a longer, more violent phase called oligarchic growth, where these embryos dominate their local zones and slowly accrete the remaining smaller bodies. And then, in the inner solar system at least, the final stage is a period of giant impacts. These Mars-sized embryos crashing into each other in collisions of almost incomprehensible violence, and it's precisely one of these collisions that gives us the Moon. Let's talk about that for a second, because the origin of the Moon is one of the great detective stories in planetary science. For a long time, there were competing hypotheses. Maybe the Moon was captured, a wandering body that got snagged by Earth's gravity. Maybe the Earth and Moon formed together as a double system. Maybe a fast-spinning early Earth flung off a piece of itself. None of these worked cleanly. Captured moons should have different compositions than their host planets, but the Moon's oxygen isotope ratios are nearly identical to Earth's. Co-formation doesn't explain why the Moon has such a tiny iron core compared to Earth, and the fission idea has angular momentum problems. The hypothesis that eventually won out, and it's still the leading model today, is the giant impact hypothesis. In the mid-1970s, William Hartmann and Donald Davis proposed it, and independently, Alistair Cameron and William Ward developed a similar idea. The scenario goes like this. About 4.5 billion years ago, roughly 50 to 100 million years after the Sun formed, a Mars-sized body, sometimes called Theia, after the Greek Titaness who was the mother of the moon goddess Selene, slammed into the young Earth at an oblique angle. The collision was catastrophic. It would have melted most or all of Earth's surface, vaporized a significant fraction of both bodies, and ejected an enormous cloud of superheated rock and metal into orbit around the Earth. That cloud of debris, within perhaps just a few decades or centuries, coalesced into the Moon. And here's what's really clever about this model. It explains so many things at once. It explains why the Moon's composition is so similar to Earth's mantle, because the debris came mostly from the outer layers of both bodies. It explains why the Moon is depleted in iron, because the iron cores of both Earth and Theia mostly ended up in the merged Earth's core rather than in the ejected debris. It explains why the Moon has very few volatile elements, water, sodium, potassium, because those would have been boiled away in the superheated aftermath of the impact. And it explains the angular momentum of the Earth-Moon system. It's one of those beautiful cases where a single hypothesis cleans up a whole mess of puzzles at once. Now, the details are still being debated. More recent simulations, including work by Sarah Stewart and Mattia Chuk around 2012, have suggested variations. Maybe the impact was more energetic than originally thought. Maybe it created a structure called a synestia, which is essentially a donut-shaped cloud of vaporized rock that the Earth and Moon both condensed out of. This could explain why the isotopic compositions are so eerily similar. If both bodies formed from the same well-mixed cloud, you'd expect them to be nearly identical. The story isn't fully settled, but the broad picture, a giant impact creating the Moon, is one of the most robust ideas in planetary science. And that Moon matters. It matters a lot more than you might think, and not just for tides and romantic evenings. The Moon stabilizes Earth's axial tilt. Right now, Earth is tilted about 23.4 degrees relative to its orbital plane, and that tilt is what gives us seasons. Without the moon's gravitational influence, Earth's tilt would wobble chaotically over millions of years, swinging from nearly zero, which would eliminate seasons, to perhaps 45 degrees or more, which would create extreme seasonal variations that might make complex life very difficult. Mars, which has no large moon, actually does experience this kind of chaotic obliquity variation, and its tilt has probably swung wildly over its history. So our moon may be one of the reasons Earth has been a stable enough environment for life to evolve. It's a remarkable thought that a random collision 4.5 billion years ago might have been a prerequisite for your existence. So now we have a young Earth, freshly formed, still glowing from the heat of accretion and that giant impact, with a brand new moon hanging close. Much closer than it is today, because the moon has been slowly spiraling outward ever since, driven by tidal interactions. In those early days, the moon would have looked enormous in the sky, and the Earth was spinning much faster. A day might have been only 6 hours long. The surface was largely or entirely molten, a magma ocean hundreds of kilometers deep, and the atmosphere was thick with steam and carbon dioxide and other volcanic gases. It's a hellscape, really, and geologists actually call this period the Hadean Eon, named after Hades, the Greek underworld. Fitting. But here's the thing about the Hadean. It didn't last as long as we used to think. For decades, the assumption was that the first several 100 million years of Earth's history were just unrelenting bombardment and molten chaos, completely inhospitable to anything resembling life. But evidence has been accumulating that the Earth cooled faster than expected. The oldest known minerals on Earth are tiny crystals of zircon found in the Jack Hills of Western Australia, and some of these zircons have been dated to about 4.4 billion years ago, just 150 million years after the Earth formed. And here's what's remarkable about them. Their chemistry suggests they crystallized in the presence of liquid water. Not steam, not magma, liquid water. Which means that within just a couple 100 million years of that apocalyptic giant impact, Earth had cooled enough to have oceans, or at least bodies of liquid water on its surface. And if there was liquid water that early, then the stage was set for something else. Something that might be the most profound transition in the entire history of the universe, or at least the most profound one we know about. Because somewhere on this young, cooling, water-covered world, chemistry was about to become biology. The question of how life began, abiogenesis, the origin of life from non-living matter, is one of the deepest unsolved problems in all of science, and it sits right at the intersection of chemistry, geology, biology, and physics. We don't know exactly how it happened. We don't know exactly when. We don't even know exactly where. But we have clues, and some of them are really fascinating. Let's talk about them. So picture this young Earth, maybe 4 billion years ago, give or take. The heavy bombardment is tapering off, though impacts still happen. The atmosphere is nothing you'd want to breathe. Mostly carbon dioxide, nitrogen, maybe some methane, traces of other volcanic gases. No free oxygen to speak of. The oceans are there, warm, maybe even hot in places, laced with dissolved minerals and metals. And everywhere, in the water, in the atmosphere, on the surfaces of rocks, simple chemistry is happening. Molecules are forming, breaking apart, recombining. Carbon atoms are linking up with hydrogen, oxygen, nitrogen, sulfur. Nothing alive, not yet, but the raw ingredients are swirling around in staggering variety. The fundamental question is this: how do you get from simple molecules, water, carbon dioxide, ammonia, methane, to something that can copy itself, that can metabolize, that can evolve. How do you cross that threshold? Because when you really think about what even the simplest living cell does, it's astonishing. Even a basic bacterium is a fantastically complex chemical machine. It has a membrane that separates inside from outside. It has DNA or RNA that stores information. It has proteins that catalyze reactions. It has metabolism. It takes in energy and raw materials from the environment and uses them to maintain and reproduce itself. Getting all of that from scratch, from just rocks and water and simple gases, that seems almost impossibly hard. And honestly, it is hard. That's why it's still unsolved. But we've made remarkable progress in understanding how individual pieces of the puzzle might have fallen into place, and the story that's emerging is genuinely beautiful. One of the earliest and most famous experiments in this whole field happened in 1953 at the University of Chicago. A graduate student named Stanley Miller, working with his advisor Harold Urey, set up an elegantly simple apparatus. They filled a flask with gases they thought represented Earth's early atmosphere, methane, ammonia, hydrogen, water vapor, sealed it up, and then zapped it with electrical sparks to simulate lightning. They let it run for a week, and when they analyzed the brownish gunk that collected in the water trap at the bottom, they found amino acids, glycine, alanine, several others. The building blocks of proteins, synthesized from scratch in a laboratory simulation of early Earth conditions. The Miller-Urey experiment was electrifying. It made headlines. It seemed to suggest that the chemistry of life was almost inevitable. Just add energy to the right gases and the building blocks practically assemble themselves. Now, in the decades since, our understanding of Earth's early atmosphere has shifted. Most researchers now think it was less reducing than Miller assumed, more carbon dioxide and nitrogen, less methane and ammonia. And when you repeat the experiment with a more realistic atmosphere, you still get organic molecules, but the yields are lower. So the picture is more nuanced than that first flush of excitement suggested. But the core insight holds. The basic molecular building blocks of life are not hard to make. They form readily under a wide range of conditions. In fact, amino acids have been found in meteorites. The Murchison meteorite that fell in Australia in 1969 contained over 70 different amino acids, most of them not used by life on Earth. So the universe is apparently quite good at making these molecules. The raw materials were never the hard part. The hard part, the really hard part, is what comes next. How do you get from a soup of amino acids and other simple organic molecules to something that's actually alive? And this is where it gets genuinely interesting, because there are several competing hypotheses, each with real evidence behind it, and the debate is still very much alive. One of the most influential ideas is called the RNA world hypothesis. Here's the logic behind it. In modern life, you have this chicken and egg problem. DNA stores genetic information, but it needs proteins to replicate and express that information. Proteins do the actual chemical work of the cell, but they're built according to instructions encoded in DNA. So which came first? You can't have one without the other, it seems. But in the early 1980s, Thomas Seck and Sidney Altman independently discovered something remarkable, that RNA, ribonucleic acid, can act as both an information carrier and a catalyst. Certain RNA molecules, called ribozymes, can catalyze chemical reactions, including, and this is the key part, the copying of other RNA molecules. So RNA can do double duty. It can store information like DNA, and it can catalyze reactions like proteins, which means, in principle, you could have a self-replicating system made entirely of RNA, no DNA or proteins needed, a simpler, earlier form of life running on RNA alone. This idea, the RNA world, has become one of the leading frameworks for thinking about the origin of life. And there's good circumstantial evidence for it. The ribosome, that molecular machine inside every living cell that reads genetic instructions and builds proteins, is fundamentally an RNA machine. Its catalytic core is made of RNA, not protein. The proteins are structural scaffolding. The RNA does the actual work. That looks very much like a fossil, a molecular relic of an earlier era when RNA ran the show. But the RNA world has its own problems. RNA is a complicated molecule. Its backbone involves ribose, a sugar that's not trivially easy to synthesize under prebiotic conditions. For years, this was a major stumbling block. How do you get RNA to form spontaneously? Then in 2009, John Sutherland and his colleagues at the University of Manchester published a landmark paper showing that you could synthesize RNA nucleotides, the individual units that link together to form RNA, from very simple precursor molecules through a plausible series of chemical steps, without ever needing to make ribose as a separate intermediate. The chemistry was elegant, and it reinvigorated the RNA world camp. But we're still a long way from demonstrating a fully self-replicating RNA system emerging spontaneously from prebiotic chemistry. It remains a hypothesis, a very good one, but a hypothesis. Now there's a whole other school of thought that approaches the problem from a different direction entirely, and it focuses not on information and replication, but on energy and metabolism. This is sometimes called the metabolism first view, and one of its most compelling versions centers on a very specific kind of environment: alkaline hydrothermal vents on the ocean floor. You might have heard of hydrothermal vents, those dramatic black smokers that shoot superheated mineral-laden water into the deep ocean. Those were discovered in 1977 along the Galapagos Rift, and they host incredible ecosystems powered not by sunlight, but by chemical energy. But the vents we're talking about here are different. They're not the scorching hot black smokers. They're a gentler, cooler variety called alkaline vents. And the best-known example is a formation called the Lost City, discovered in the year 2000 on the Mid-Atlantic Ridge. Lost City vents are powered by a chemical reaction called serpentinization, where seawater reacts with a type of rock called olivine. The fluid coming out is warm, not boiling, maybe 40 to 90 degrees Celsius. And it's highly alkaline, rich in hydrogen gas and simple organic molecules. Here's what's really clever about the alkaline vent hypothesis, championed most prominently by the geochemist Mike Russell and later elaborated by Nick Lane and others. These vents naturally create tiny mineral compartments, microscopic pores and chambers in the rock, separated by thin mineral walls. And across those walls, you get a natural chemical gradient. The alkaline vent fluid on one side, the more acidic ocean water on the other. That gradient, that difference in proton concentration, is essentially a natural battery. And here's the kicker. Every living cell on Earth today powers itself using exactly this kind of proton gradient. It's called chemiosmosis, and it was discovered by Peter Mitchell, who won the Nobel Prize for it in 1978. In your mitochondria, right now, as you lie there, protons are being pumped across membranes, and the flow of those protons back through a molecular turbine called ATP synthase is what generates the ATP that powers virtually everything your cells do. The fact that all life uses this same fundamental mechanism, proton gradients across membranes, suggests it might be very ancient indeed. And alkaline vents provide it for free. No biology required, so In this picture, life didn't start with a self-replicating molecule floating in some warm pond. It started in the rocky labyrinth of an ocean floor vent, where natural chemical gradients provided the energy, mineral surfaces provided the catalysis, and tiny compartments provided the containment. Metabolism came first, and the information-carrying molecules, RNA, eventually DNA, came later, as the system became more sophisticated. Which view is right? Honestly, we don't know yet. And it's entirely possible that the real answer involves elements of both, that the chemistry of self-replication and the chemistry of energy metabolism converged in some environment we haven't fully reconstructed yet. There are other ideas too. Some researchers have focused on the role of clay minerals as templates for organizing organic molecules. Others have looked at ice. The concentration of molecules in tiny liquid veins within sea ice could have driven reactions that are too dilute to happen in open water. There's even the panspermia idea, which doesn't really solve the problem so much as relocate it. Maybe life's building blocks, or even primitive life itself, arrived on Earth aboard meteorites or comets. We know organic molecules survive in space. We know meteorites deliver them. But even if the ingredients came from space, the assembly still had to happen somewhere. What we do know, and this is the part that always gets me, is that whatever happened, it happened relatively fast in geological terms. The oldest widely accepted evidence for life on Earth comes from carbon isotope signatures in rocks from Greenland, the Isua supracrustal belt, dating to about 3.7 billion years ago. There are claims of even older evidence, possible microfossils in rocks from the Nouveau-Guitok belt in Quebec that might be 4.28 billion years old, though that's hotly debated. But even taking the conservative estimate, life was established by 3.7 billion years ago, which means it arose within the first billion years of Earth's existence, and possibly much sooner. Given that the planet was largely molten for its first 100 million years or so, and then subject to intense bombardment, the window for life to emerge might have been remarkably narrow. Some people find that unsettling. How could something so complex arise so quickly? Others find it encouraging. Maybe the chemistry of life isn't as improbable as it seems. Maybe, given the right conditions, it's almost inevitable. And once life did get started, even in its most primitive form, some tiny membrane-bound packet of self-sustaining chemistry, huddled around a hydrothermal vent or clinging to a mineral surface, evolution took over. And evolution, given enough time and enough variation, is extraordinarily creative. But for the first couple of billion years, life on Earth was entirely microbial, single-celled organisms, bacteria and archaea. No plants, no animals, no fungi. Just microbes everywhere, doing an incredible diversity of chemistry. And among those early microbes, one group stumbled onto an innovation that would literally transform the planet, reshape the atmosphere, and eventually make complex life possible. They figured out how to split water molecules using sunlight, and in doing so, they released a gas that was, at the time, a deadly poison to almost everything else alive. That gas was oxygen, and the organisms responsible were cyanobacteria. Tiny, unassuming, single-celled organisms that you can still find today in ponds, in oceans, in hot springs, forming those slimy green mats on rocks. They look like nothing special, but cyanobacteria are arguably the most consequential life form in the entire history of Earth. What they did, what they're still doing, changed everything. Let's talk about what made them so revolutionary, because the chemistry here is genuinely beautiful. Before cyanobacteria, photosynthesis already existed in a simpler form. Earlier microbes had figured out how to capture light energy and use it to drive chemical reactions, but they used molecules like hydrogen sulfide or iron as their electron donors, the raw material they pulled apart to fuel the process. These molecules worked fine, but they were limited in supply. You had to be near a volcanic vent or a particular mineral deposit to find them. Cyanobacteria figured out how to use water instead. And water, well, water was everywhere. It was the most abundant molecule on the planet's surface. But splitting water is hard. It takes a lot of energy. The oxygen atoms in water are bound tightly to their hydrogen partners, and prying them apart requires a sophisticated molecular machine. Cyanobacteria evolved exactly that machine, a protein complex called photosystem II, which uses the energy of sunlight to rip electrons away from water molecules, one at a time. When you strip the electrons and hydrogen away from water, what's left over is oxygen, O2. And cyanobacteria just released it, breathed it out, essentially. It was waste to them, a byproduct. Here's the thing, though. Oxygen is a ferociously reactive molecule. It wants to bond with almost everything. It attacks organic molecules, disrupts cellular chemistry, corrodes metals. For the anaerobic organisms that dominated early Earth, microbes whose entire metabolism was built around an oxygen-free world, this stuff was poison, genuinely toxic. So when cyanobacteria started producing oxygen, they were essentially dumping industrial waste into the environment. And at first, it didn't matter much because the Earth had an enormous capacity to absorb that oxygen before it could accumulate in the atmosphere. The oceans were full of dissolved iron, billions of tons of it, and oxygen reacted with that iron almost immediately, forming iron oxides that sank to the seafloor. This is actually where banded iron formations come from, those beautiful striped rocks you see in geology museums, alternating layers of iron-rich and iron-poor sediment. They're found all over the world. The Hamersley Basin in Western Australia, the Masabi Range in Minnesota, the Transvaal Supergroup in South Africa. These formations are literally the geological record of oxygen being produced and then immediately captured. The atmosphere stayed essentially oxygen-free even while cyanobacteria were churning the stuff out because the planet's iron was soaking it up like a sponge. But sponges fill up. And somewhere around 2.4 billion years ago, give or take, the dissolved iron was largely used up. The oxygen sinks were saturated, and suddenly, oxygen began to accumulate in the atmosphere with nothing left to absorb it. This is the Great Oxidation Event, sometimes called the GOE, sometimes called the oxygen catastrophe, depending on your perspective. If you were a cyanobacterium, it was a triumph. If you were an anaerobic microbe, it was an apocalypse. The evidence for the GOE is written in the rocks in several ways, but one of the most compelling involves a mineral called pyrite, iron sulfide, fool's gold. Before the GOE, you find rounded grains of pyrite in river sediments, meaning it was being weathered and transported by water without being destroyed. Pyrite is unstable in the presence of oxygen. It rusts, basically. So the fact that it survived long enough to be tumbled smooth in riverbeds tells you the atmosphere had essentially no free oxygen. After about 2.4 billion years ago, detrital pyrite disappears from the geological record. It couldn't survive anymore. The air had changed. Another line of evidence comes from sulfur isotopes, specifically something called mass-independent fractionation of sulfur, which is a mouthful, but the idea is elegant. Certain photochemical reactions in the atmosphere can sort sulfur isotopes in unusual ways, but only if there's no ozone layer, and there's no ozone layer if there's no oxygen. before 2.4 billion years ago, you see this anomalous sulfur signal in the rocks. After 2.4 billion years ago, it vanishes. The ozone layer had formed. Oxygen was in the air to stay. Now, the consequences of this were staggering. Most of the existing biosphere, the anaerobic organisms that had been running the show for over 1 billion years, was devastated. They didn't go extinct entirely. Many retreated to oxygen-free niches, deep sediments, the guts of other organisms, hydrothermal vents. Their descendants are still there today, but they were pushed to the margins. The world belonged to organisms that could tolerate oxygen, and eventually to organisms that could use it. And here's where something really clever happened. Something that connects back to that idea of evolution being extraordinarily creative when given time. Some cells didn't just learn to tolerate oxygen, they learned to harness it. Aerobic respiration, the process your own cells use right now as you lie there breathing, is essentially the reverse of photosynthesis. Photosynthesis uses light energy to split water and store that energy in sugar molecules. Aerobic respiration takes those sugar molecules, combines them with oxygen, and releases that stored energy. And it releases a lot of it. Aerobic respiration extracts roughly 18 times more energy from a molecule of glucose than anaerobic fermentation does. 18 times. Think about what that means. Suddenly, cells had access to an enormously more powerful energy source. They could do more, build more, sustain more complex structures. Oxygen didn't just change the atmosphere, it raised the energy ceiling for life itself. But we're still talking about single cells here. Bacteria. Archaea. For another 1 billion years or so after the Great Oxidation event, that's mostly what life remained. This stretch of time, from roughly 1.8 to 0.8 billion years ago, is sometimes called the boring billion, which is a little unfair, but the name has stuck. The climate was relatively stable. Oxygen levels were low compared to today, maybe a few % of modern levels, and the fossil record is sparse. It looks at first glance like nothing much was happening, but something was happening, something enormous. Because somewhere during this period, and the exact timing is debated, but current estimates center around 1.5 to 2 billion years ago, one of the most important events in the history of life occurred. A single-celled organism, probably an archaeon, engulfed a bacterium. And instead of digesting it, the bacterium survived inside the host cell. It kept living, it kept metabolizing, and over time, the two organisms became so dependent on each other that neither could survive alone. The bacterium became a permanent internal resident, an organelle. That bacterium was the ancestor of mitochondria, the tiny power plants inside your cells right now, the organelles that perform aerobic respiration, that use oxygen to generate the energy currency your body runs on. This is endosymbiosis, and the person who championed this idea most forcefully was Lynn Margulis. She published her landmark paper in 1967, and it was rejected by about 15 journals before the Journal of Theoretical Biology finally accepted it. The scientific establishment thought she was wrong. The idea that a fundamental component of our cells was once a free-living bacterium seemed too strange, too radical. But the evidence accumulated. Mitochondria have their own DNA, their own double membrane. They replicate independently of the cell. Their ribosomes resemble bacterial ribosomes. Margulis was right, and her insight is now one of the cornerstones of cell biology. And it happened again. A eukaryotic cell, one that already had mitochondria, engulfed a cyanobacterium. And that cyanobacterium became the chloroplast, the organelle that performs photosynthesis in every green plant and alga on Earth today. So the cyanobacteria didn't just transform the atmosphere from the outside. Some of them were literally incorporated into other cells, carrying their photosynthetic machinery with them. Every leaf you've ever seen, every blade of grass, every piece of lettuce, every giant redwood, they're all running on captured cyanobacteria, layers upon layers of evolutionary inheritance, the emergence of eukaryotic cells, complex cells with internal compartments, a nucleus, mitochondria, and in some lineages chloroplasts, was a threshold moment. These cells were bigger, more energy-rich, and more structurally complex than anything that came before. And they opened the door to something that bacteria and archaea had never achieved on their own. True multicellularity. Not just clumps of identical cells sticking together, but differentiated organisms where different cells take on different roles, some becoming skin, some becoming nerve, some becoming muscle, coordinated, integrated, complex bodies. But multicellularity didn't happen overnight, and it didn't happen just once. It evolved independently dozens of times, in animals, plants, fungi, algae, even in some bacteria. Each time, it required solving the same basic problems. How do cells communicate with each other? How do you ensure cooperation when any individual cell could theoretically cheat, grow faster, ignore the rules, essentially become a cancer? How do you coordinate a body? The earliest fossils that might represent large, complex, multicellular life come from the Ediacaran period, starting around 635 million years ago, after the planet emerged from one of its most extreme climate episodes, the snowball Earth glaciations, when ice may have extended all the way to the equator. The connection between those glaciations and the subsequent explosion of complex life is tantalizing but not fully understood. Some researchers think the glaciations drove evolutionary innovation by creating extreme selective pressure. Others think the key factor was a second major rise in atmospheric oxygen, sometimes called the Neoproterozoic oxygenation event, which may have finally pushed oxygen levels high enough to support large, active, multicellular bodies. The Ediacaran fossils are strange and wonderful. Dickinsonia, a flat, ribbed organism that could grow over a meter across, looking like a quilted bath mat. Kimberella, which might be an early mollusk relative. Charnia, a frond-like form that lived in deep water, too deep for photosynthesis, filter feeding or absorbing nutrients in ways we still don't fully understand. These organisms don't fit neatly into any modern category. Some paleontologists think they represent a completely separate experiment in complex life, one that mostly went extinct before the familiar animal body plans emerged. And then, around 540 million years ago, the Cambrian explosion. In a geologically brief window, maybe 20 to 25 million years, which sounds long but is a blink in deep time, nearly all the major animal body plans that exist today appeared in the fossil record. Eyes, legs, shells, claws, nervous systems, guts, segmented bodies. The Burgess Shale in British Columbia, discovered by Charles Walcott in 1909, preserves an astonishing snapshot of this moment. Anomalocaris, a meter-long predator with grasping appendages and compound eyes. Hallucigenia, so bizarre it was originally reconstructed upside down and backwards. Opabinia, with 5 eyes and a forward-facing nozzle that looks like something from science fiction. The Chengjiang fauna in China's Yunnan province, slightly older, tells a similar story of sudden, riotous diversification. What triggered the Cambrian explosion is one of the great open questions in paleontology. Rising oxygen levels, the evolution of predation, creating an arms race, the development of eyes enabling new ecological interactions, changes in ocean chemistry, probably all of these and more, feeding back on each other in ways we're still untangling. But the result was unmistakable. Life went from mostly simple and mostly microbial to spectacularly, bewilderingly complex. And from that point forward, the story accelerates. Mass extinctions and recoveries, the colonization of land, the rise of forests, the age of dinosaurs, the asteroid impact 66 million years ago that cleared the stage for mammals, and eventually, on one particular branch of one particular lineage of primates, the emergence of a species that would look up at the stars and wonder where it all came from. And that wondering, that impulse to look up and ask why, is itself part of the story. Not separate from it, not floating above it, woven right into the fabric of everything we've been talking about tonight. So let's stay with that thread for a little while longer. Because the journey from the Cambrian explosion to you, lying here right now, is in some ways the fastest stretch of the whole story, and in other ways, it's the richest. 540 million years. Sounds like a lot. But remember, the universe is almost 14 billion years old. The stretch from the Cambrian to this moment is less than 4% of cosmic history. Everything you think of when you think of complex life on Earth, fish, forests, dinosaurs, flowers, birds, whales, cities, all of it fits into that thin sliver at the very end, and it wasn't a smooth ride. Not even close. Life diversified in extraordinary bursts, and then, again and again, it was nearly annihilated. There have been at least 5 major mass extinctions in the last 500 million years, events so catastrophic that they each wiped out a significant fraction of all species on Earth. The worst of them, the Permian-Triassic extinction about 252 million years ago, killed something like 90 to 96% of all marine species and around 70% of terrestrial vertebrate species. 96%. Imagine a world where almost everything alive simply stops being alive. The oceans went largely anoxic. Massive volcanic eruptions in what's now Siberia, the Siberian Traps, poured out lava over an area roughly the size of Western Europe, releasing staggering quantities of carbon dioxide and sulfur dioxide, acidifying the oceans, destabilizing the climate. It took millions of years for ecosystems to recover. Some paleontologists call it the Great Dying, and the name fits. But here's the thing about mass extinctions, and this is one of those ideas that's both terrible and beautiful at the same time. They destroy, yes, indiscriminately and catastrophically. But they also clear ecological space. They remove dominant groups and open niches for survivors to radiate into. The Permian-Triassic extinction, devastating as it was, set the stage for the rise of the archosaurs, the lineage that would eventually produce dinosaurs, pterosaurs, and crocodilians. Without that catastrophe, the Mesozoic world might have looked completely different. The dinosaurs might never have had their chance. And the dinosaurs, let's talk about them for a moment, because they deserve it. They dominated terrestrial ecosystems for over 160 million years. That's an almost incomprehensible reign. For context, our genus, Homo, has been around for maybe 2 to 3 million years. Modern humans, Homo sapiens, about 300,000. The dinosaurs had us beat by a factor of more than 500. They weren't the lumbering, dim-witted creatures of old Hollywood movies. Many were warm-blooded, or at least something close to it. Some were covered in feathers. We know this from extraordinary fossils preserved in fine-grained sediments in places like Liaoning Province in China, where you can see the impressions of feathers as clearly as if they'd been pressed into the rock yesterday. Velociraptors had feathers. Microraptor had 4 wings. The boundary between dinosaurs and birds isn't really a boundary at all. Birds are dinosaurs, technically. They're the one lineage of theropod dinosaurs that survived what came next. What came next was the Chicxulub impact, 66 million years ago. An asteroid roughly 10 to 12 kilometers across, about the size of a small city, struck what is now the Yucatan Peninsula in Mexico at something like 20 kilometers per second. The energy released was on the order of 10 billion Hiroshima bombs. Think about that number for a second. 10 billion. The impact punched a crater nearly 180 kilometers wide. It sent a plume of superheated rock and dust into the upper atmosphere. Within hours, debris raining back down heated the atmosphere enough to ignite wildfires across much of the planet. Soot and sulfate aerosols blocked sunlight for months, maybe years. Photosynthesis collapsed. Global temperatures plummeted, then later spiked from greenhouse gases released by the impact and by massive volcanic activity in India's Deccan Traps that was already underway. The oceans acidified. Food chains disintegrated from the bottom up. About 75% of all species went extinct, including every non-avian dinosaur. It was, in a very real sense, the worst day in the history of complex life on Earth. There's a thin layer of clay in the geological record, found all over the world, right at the boundary between the Cretaceous and the Paleogene periods. It's enriched in iridium, an element rare on Earth's surface, but common in asteroids. Luis and Walter Alvarez, a father-son team, one a Nobel Prize-winning physicist, the other a geologist, identified this iridium anomaly in 1980 and proposed the impact hypothesis. It was controversial at first. Many geologists resisted it, but when the Chicxulub crater was identified in the early 1990s, the evidence became overwhelming. And here's where the story turns toward you. Because in the aftermath of that catastrophe, with the dinosaurs gone and ecosystems shattered, a group of small, mostly nocturnal mammals, creatures that had been living in the ecological margins for over 100 million years, scurrying in the underbrush, eating insects, keeping out of the way of things with very large teeth, suddenly found themselves in a world with open niches everywhere. And they radiated fast. Within 10 million years of the impact, the major orders of mammals we know today had begun to diverge. Primates, rodents, carnivores, ungulates, bats, whales. All of these lineages trace their explosive diversification to the Paleocene and Eocene epochs, the tens of millions of years following the asteroid. The primates are our branch. Early primates were small, arboreal creatures, tree dwellers with grasping hands and forward-facing eyes that gave them stereoscopic vision, good for judging distances when you're leaping between branches. Over tens of millions of years, some lineages grew larger. Some developed bigger brains relative to their body size. By around 25 million years ago, the apes had diverged from the Old World monkeys. By around 6 to 7 million years ago, the lineage leading to humans split from the lineage leading to chimpanzees and bonobos, our closest living relatives, with whom we share roughly 98.5% of our DNA. What happened in those 6 or 7 million years is one of the most intensely studied and debated stories in all of science. The fossil record is fragmentary, bones and teeth mostly, preserved in the sediments of East African rift valleys and South African caves and a handful of other places. But the picture that's emerged, especially in the last few decades, is extraordinary. Our ancestors came down from the trees, or at least spent more time on the ground, and began walking upright. Bipedalism is actually one of the earliest defining features of the hominin lineage, appearing well before big brains. Australopithecus afarensis, Lucy's species, walked upright more than 3 million years ago, but had a brain not much larger than a chimpanzee's. The famous Latoli footprints in Tanzania, preserved in volcanic ash about 3.6 million years ago, look remarkably like the footprints you'd leave walking on a beach today. The big brains came later, and they came gradually, and we're still not entirely sure why. Tool use is part of the story. The earliest known stone tools date to about 3.3 million years ago from a site called Lomekwi in Kenya. Social complexity is probably part of it too. Living in groups, navigating alliances and rivalries, teaching and learning, all of these things reward cognitive ability. Climate change played a role as well. East Africa became drier and more variable over the last few million years, and adaptability, the ability to solve novel problems, to plan, to communicate, would have been a significant advantage. By about 300,000 years ago in Africa, Homo sapiens had emerged. Anatomically modern humans. People who, if you cleaned them up and put them in modern clothes, you wouldn't look at twice on the street. But anatomical modernity and behavioral modernity aren't quite the same thing. The archaeological record suggests a gradual accumulation of complex behaviors, symbolic art, personal ornaments, long-distance trade networks, sophisticated tool-making techniques, over the last few 100,000 years, with a notable acceleration in the last 100,000 or so. The oldest known cave art may be the hand stencils in Sulawesi, Indonesia, dating to at least 45,000 years ago, though some disputed dates in Spain push even earlier. The oldest known figurative sculpture is the Lion Man of Hohenstein-Stadel in Germany, carved from mammoth ivory about 40,000 years ago. Someone sat down and imagined a being that was part human, part lion, something that didn't exist in the real world, and then made it real in ivory. That's abstraction. That's imagination. That's a mind doing something genuinely new in the history of life on this planet. And then, around 70 to 60,000 years ago, groups of Homo sapiens began migrating out of Africa in significant numbers, spreading across Asia, reaching Australia by at least 65,000 years ago, which required crossing open ocean, by the way, meaning they had boats, reaching Europe by around 45,000 years ago, eventually crossing into the Americas, probably via Beringia during the last ice age, maybe 15 to 20,000 years ago, though the exact timing and routes are still actively debated. Along the way, they encountered other human species, Neanderthals in Europe and Western Asia, Denisovans in Asia, and interbred with them. If you have European or Asian ancestry, you carry about 1 to 2% Neanderthal DNA in your genome right now. It's in you. Genes that affect your immune system, your skin, your hair, inherited from people who lived in Ice Age Europe tens of thousands of years ago. About 12,000 years ago, at the end of the last ice age, something happened that would transform the planet more profoundly than any event since the Great Oxidation Event 2.5 billion years earlier. Agriculture. In several places around the world, independently, the Fertile Crescent, the Yangtze River Valley, Mesoamerica, the Andes, probably others, people began deliberately cultivating plants and domesticating animals. This wasn't a sudden invention. It was a slow, uneven transition, taking thousands of years in each region. But its consequences were revolutionary. Surplus food meant larger populations. Larger populations meant settlements, then towns, then cities. Cities meant specialization. Not everyone had to grow food, so some people could be potters, metal workers, priests, scribes, soldiers, astronomers. Writing emerged around 3200 BCE in Mesopotamia, probably initially for accounting, keeping track of grain stores and trade goods. And with writing, information could be stored outside of human memory for the first time. Knowledge could accumulate across generations in a way it never had before. And from there, and I know I'm moving fast now, but the story really does accelerate. From there, you get everything. Bronze and iron, empires and philosophy, mathematics and medicine, the printing press, the scientific revolution, steam engines and electrical grids, vaccines and antibiotics, transistors and satellites. The same curiosity that drove someone to chip a stone tool 3 million years ago eventually built the James Webb Space Telescope, which we talked about earlier tonight. That instrument floating at the L2 Lagrange point, 1.5 million kilometers from Earth, peering back in time to see the first galaxies forming after the cosmic dark ages. And here you are, right here, right now, lying in the dark, breathing quietly. Your body is made of atoms that were forged in the cores of stars that died before the sun was born. The calcium in your bones, the iron in your blood, the oxygen filling your lungs right now. All of it was cooked up in stellar furnaces and scattered across space in supernova explosions billions of years ago. The water in your cells has been cycling through this planet for 4 billion years. Some of the hydrogen atoms in your body have been around since the first few minutes after the Big Bang, when the universe was a hot, dense soup of protons and neutrons fusing into the lightest elements. You are, quite literally, the universe looking at itself. That's not poetry. Well, it is poetry, but it's also just physics. You are a collection of atoms that, through 13.8 billion years of cosmic evolution, stellar nucleosynthesis, planetary formation, chemical self-organization, biological evolution, and cultural accumulation, arrived at a configuration complex enough to be aware of its own existence, complex enough to lie in the dark and wonder about the Big Bang, complex enough to feel sleepy and comfortable and safe. The story we've traced tonight, from that unimaginably hot, dense beginning, through the first light, the first atoms, the first stars, the first galaxies, the first heavy elements, the formation of a small rocky planet around an ordinary yellow star, the emergence of life from chemistry, the slow oxygenation of an atmosphere, the invention of the eukaryotic cell, the flourishing of complex animals, the catastrophes and recoveries, the long winding path through primates and hominins to a species that paints on cave walls and builds telescopes. That entire arc is your origin story. Every bit of it. It's not something that happened to someone else, somewhere else. It happened to the matter you're made of. It happened to you. And the beautiful thing, the really beautiful thing, is that the story isn't over. The universe is still expanding. Stars are still being born in molecular clouds right now, tonight, as you drift toward sleep. Somewhere in the Milky Way, a cloud of gas and dust is collapsing, and a new star is igniting, and around it, a disk of debris is beginning to coalesce into planets. Maybe one of them, a few billion years from now, will have oceans. Maybe something will start swimming in them. But you don't need to think about that right now. You've come a long way tonight. 13.8 billion years, give or take. That's enough for one evening. The universe will still be here in the morning, doing what it does, expanding and cooling and building and destroying and building again. And you'll be here too, made of stars, breathing quietly, part of the whole grand unfolding thing. So let your eyes stay closed. Let your thoughts soften. The story will keep going. the way it always has, whether you're awake for it or not. And that's perfectly fine. That's just the universe, being the universe, the way it's been doing for a very, very long time. Rest now. You've earned it.